And so the next step in the scientific process after this shocking observation was made was, let's do some more observations to find even more, see if we can find a pattern in this. And so two other kinds of observations that I'm going to highlight are listed there. That is, more dedicated observations of these exploding stars to see if maybe there's always the potential that in your data, in your experiment, you made some sort of small mistake, a mistake that you didn't detect, you didn't realize, but mistakes are always possible. So the idea is, do more observations and double and triple check that you haven't made any mistakes. But then also try to make observations using an entirely different method and see what you get from that different method. And the idea there is that even if you've made a mistake in the first kind of detailed observation, because your second type of observation is different, you can have a sort of cross-check. And so that's what we're about to look at now, is this more dedicated observations looking for patterns. First of all, we set out and people measured more distant exploding stars. And here you see the data. And what you can see here is that the sort of greenish yellow line, I must apologize, I'm colorblind. And so by introducing, these colored plots, I may describe them incorrectly, but the line that to me looks greenish yellowish, it points to no dark energy, which was our original understanding of our universe. But you can see all of these data points, the grayish supernovas, they all are much more in alignment with that purple line, which indicates that the exploding stars do really seem to indicate that there's this presence of dark energy. Dark energy is the name that we give to this idea that the universe is accelerating in its expansion. So that was the first of the more detailed observation. The second more detailed observation is to look at the cosmic microwave background radiation, specifically looking at patterns in the CMB. So cosmic microwave background is often just shortened to CMB, and that's probably what I'll say going forward. The idea is that you take your telescope and you look at different patches of the sky and you look at this very specific wavelength of light, and you'll get these ever so small differences in different spots in the sky. Will have small patches and that are effectively different colors in these pictures. And what you would see is if you looked up and observed something that looked like this left image, that would correspond to a pattern where our universe had very little dark energy. But if you saw something that looked like this, where it's a little bit more blurred out, the spots seem to be a little bit bigger, that would correspond to a universe where there was a large amount of dark energy. So that's what you would expect for either of these two scenarios. The question now is, what do we actually observe? Well, same picture here. This is what a small amount of dark energy might look like. This is what a large amount of dark energy might look like. And this is what we actually see. So I would say that this is kind of somewhere in the middle. So we do, our CMB measurements do seem to indicate that there is dark energy. There's dark energy that is present in our universe. So that's the second of our more detailed observations. So now we made this initial observation. We followed it up with two different types of more detailed observations. And in both of these two detailed observations, they seem to confirm that there is some presence of dark energy. Now we need to try to find a pattern and make a hypothesis that explains that pattern. Before we move on to that, just a quick note that there's this, on this webpage, there's this really nice simulator that will allow you to play around with the dark energy in our universe to see how it affects what the CMB looks like. So I'd encourage you to play around with that. It's very fun. Okay, so like I mentioned, step 3, we're on to explaining the patterns that we're seeing. Well, people are clever and they've come up with many different ideas. The first hypothesis is what was called the vacuum energy. The second hypothesis is the idea that maybe our understanding of gravity gravity is what dictates what happens on very large scales like stars and galaxies. Maybe it needs to be changed a little bit. Maybe our understanding of gravity is not correct. Or yet another hypothesis is that maybe there's just this entirely new substance out there, and this entirely new substance might be what's the answer for dark energy. I've just listed two different examples. One goes by quintessence, the other is Chaplygin gas. These are all of these are all different hypotheses of what might be the explanation for dark energy. Let's look at these one by one. Well, the next step in the scientific process is once you have a hypothesis, that's not good enough, right? That's just a proposed explanation. So what you have to do is set out and do a dedicated experimental test of that hypothesis. Ideally, your experimental test of that hypothesis is testing that idea or testing that hypothesis in an entirely different setting. So let's look at that. Let's start with vacuum energy. It turns out that there's a way to test this in the lab through something that is called the Casimir effect. And so people have been doing this for a while, for about 30 years. So let me describe what's going on here. Before I do that, talking about modified gravity was our second sort of hypothesis. You can also test that in the lab by doing a very detailed test of the gravitational force or a specific aspect of it. And then the new types of fields, well, those are actually quite hard to test. And so I'm welcome to any ideas you have. We'll go and try to build one in the lab. All right. But let's look in detail, at least at tests of hypothesis 1 and 2. So let's start with hypothesis 1, that maybe it's the vacuum energy. Well, first of all, what do we mean by that? Vacuum energy is the idea that even if you went into outer space, into the middle of nowhere outer space, where there's absolutely nothing at all, absolutely not one thing at all, you still have this very interesting effect that comes out because of the what quantum mechanics tells us. And it effectively says that even in the middle of nowhere, you constantly get a situation where particles and antiparticles are creating out of thin air. They're created for a very short time, and then they destroy each other. They create and then destroy, and create and then destroy. And this process leads to the fact that it turns out that even in the middle of nowhere, outer space, where there's absolutely nothing, there's no regular normal particles, no nothing, we have the presence of some amount of energy. And we call that energy the vacuum energy. It's a very strange concept. To be honest, it's still something that I find a little bit goofy, but it seems to be there because it is something that we can test. And so since vacuum is what most of outer space is, it would make sense that the vacuum energy might be what's causing dark energy. So people have done experiments on this, and they call these experiments measurements of the Casimir effect. The idea is you take two metal plates, you put them very close to each other. And it turns out that what happens is all those particles and antiparticles that I was talking about, if you look at the region between the plates, this small region between the plates, that you don't get as many of those particles and antiparticles popping into existence in it. There's some fundamental limitation to how many particles and antiparticles can create in this space. But outside the plate, there's no limitation to that. And so what that means is you get more particles and antiparticles creating and destroying each other on the outside of the plate than you do on the inside. And that difference between the outside and the inside gives rise to these plates actually being forced together. And that fact that those plates get forced together is called the Casimir effect. And this has been measured. And it turns out that when you measure this, it's a measurement of the vacuum energy. But the bad news is the amount of vacuum energy that we measure is 10 to the power 120 times too much to be dark energy. That is a 10 with 120 zeros after it. So this is so far off what we see from dark energy. It just doesn't seem possible anymore that the Casimir effect could be what, or that the vacuum energy is what could be explaining dark energy. So this seems to be, this experiment is inconsistent with our hypothesis. That is the hypothesis of vacuum energy. So it seems like we need to rule that hypothesis out.